Welcome back. In this video, we're going to continue with Chapter 7, and we're going to focus on the reversible expansion of ideal gases. Now, our motivation here is that when we looked at the heat and workflow during some process, we understood that those were path integrals, and those path integrals are not going to be easy to solve, particularly if we're dealing with an irreversible process. But the important thing to understand in thermodynamics is that our state functions are independent of the history. So if I have a state A at equilibrium and a state B at equilibrium, how I connect those states, whether it's reversible or irreversible, doesn't matter. All that matters, if I want to know the difference in a state function, the difference between the enthalpy of A and B or the internal energy of A and B, only depends upon their initial and final states. It doesn't depend on the path. So if I connect them in an irreversible process and I want to know the difference in the state function, well, it's going to be exactly the same difference if I connect them in a reversible process. So the way we look at evaluating the path integrals during irreversible processes is to find a reversible process that connects the same two states, and that will give us our change in that particular state function for that irreversible process. Even though we didn't have to evaluate through that actual irreversible process, we just find an equivalent reversible process that takes us between those same two states and allows us to calculate that delta U or delta S or delta H, for that process. Okay, so let's take a look now at how we would calculate the changes in state functions for reversible expansion of an ideal gas. So what's important is that when you write down a path integral, for example here's a path integral for expansion or compression for the work. So we know we have minus the integral of PdV, and it depends on some path. If we're in a reversible process, then we know that the pressure at every point along the way is an equilibrium pressure for that system. So if we were dealing with an ideal gas, then we know the equation of state that tells us what that equilibrium pressure is, and that's PV equals nRT, right? So we can substitute in for the pressure, the equilibrium pressure, nRT over V, and that is going to tell us for a reversible process what our path, how our path is going to vary. So this is for, I'm going to put over here in parentheses that the conditions under which this equation applies. And so this assumption, this here assumes that we're dealing with an ideal gas and that we're working with a reversible process, and that reversible process allowed us to substitute nRT over V for P here, assuming that we're always at equilibrium here. So what I'm going to do then is to start from here, and I'm going to examine a couple cases. I'm going to examine isothermal reversible expansion of an ideal gas. I'm also going to examine adiabatic reversible expansion of an ideal gas. And then from these, we're going to draw conclusions about what happens during an irreversible expansion of a gas in a vacuum. So let's start with the isothermal expansion of an ideal gas. So what's important first is that during an isothermal process, the temperature remains constant during the entire process. So that means that if we go back to this previous slide here, this temperature is going to stay constant throughout the process, which means it can slide out of the integral. So when we've done exactly that, we've slid out the temperature, and of course the gas constant can slide out, and it's a closed system, so the number of moles is staying constant. So we take everything out of the integral, and all we're left inside the integral is dV over V. And now we have an integral that we can evaluate, and just remember your basic calculus, we see that integral evaluates to the log of V final over V initial. So there we have an expression that the work that we get for a reversible isothermal expansion of an ideal gas is simply equal to minus nRT log of V final over V initial. And again, this is our assumptions that went into calculating this result. All right. Now, we also learned in the chapter on kinetic theory of gases that the internal energy is linearly proportional to the temperature, right? It was just 3/2 RT in that case for a monatomic gas. So what we know then is that if the temperature is constant, if we have an isothermal process, delta T is 0, that would imply then that delta U has to be equal to 0 too. So that means the first law tells us that delta U, which we now know is 0, is equal to the heat flow plus the work, the energy that went through as work, and so that means that Q must be equal to minus W. So now that we've calculated the work, that tells us that the heat that flowed during this isothermal process is equal to the same expression, except now it has the opposite sign, nRT log of V final over V initial. So what's happening during this reversible process? You can imagine we have a piston cylinder apparatus and it's immersed in some kind of constant temperature bath. As it expands, it's losing energy as work, and that's the energy we're losing. But at the same time, heat is being drawn into our piston cylinder from the temperature bath, the constant temperature bath, and that's replacing the energy that's lost during work, so that the net change in the internal energy is zero for our ideal gas during this reversible process. So that was what happens here. So we have the work, which is this expression, and we have the heat, that's this expression, and we know for the ideal gas that delta T is equal to 0, and so we know that delta U is equal to 0. Okay, this is a pretty simple case, and again, this is for the ideal gas. We'll talk about real gases later, but this is what we know to be true from just doing this simple path integral, which we can now simplify with the equation of state in a reversible process. Okay. Now let's next look at an adiabatic expansion of an ideal gas, and this one's going to be trickier, okay, because now when we expand a gas adiabatically, there's no bath surrounding it, so there's no heat that can flow in and out of the system. So as the system expands, it's going to do work, so it's going to lose energy, and since there's no heat flow to replace that energy loss like we did in the previous example when it was isothermal, in an adiabatic case it expands, it's producing work, so that the work is negative, its energy has to be going down, its temperature is also going to be going down because the energy is going down, so we can't factor the temperature out of the integral like we did before. So in this case, you see here, if we do an adiabatic expansion, if we do it reversibly, then we can still use PV equals nRT, but the temperature is going to be changing as it expands. So we can't factor it out of the integral like we did in the previous example here. So we have to take a different approach. So what we're going to do is we're going to go back to the first law. We're going to see that du is equal to dq plus dw, but since it's adiabatic process, so no heat can flow in and out of the system, then we know that dq is equal to 0. So whatever work that we get out of the system, that work is how much the energy gets dropped, the internal energy gets dropped. So we can do a few tricks here. What we're going to do is first we're going to rearrange, we're going to use our constant volume heat capacity here, and we're going to write du is equal to CV dt, which has to be equal to the work here, which we know is going to be, the differential work is going to be minus PdV. So that allows us to rearrange this expression and put CV dt over here, and then rearrange over here with our ideal gas law for P over here, and we get an expression that we can now rearrange, bring the temperature part over to this side and the volume part over to this side, and now we have two integrals we can evaluate. Now, generally, we would expect that the heat capacity might be temperature dependent, but what we're going to do is assume that the heat capacity is temperature independent in the range that we're looking at. Now, we're also looking at an ideal gas, so we know in an ideal gas, actually the heat capacity is independent of temperature, but in general, for a real gas, the heat capacity can depend upon temperature. But in this case, we're valid in taking the CV out of the integral and just giving us the simple result for evaluating the integral of dt over t from ti to tf, and gives us this result. Similarly over here, on the volume side, we only have the integral dv over v, which evaluates to ln of v final over v initial. All right. So rearranging this expression here, I'm going to do a trick. I'm going to take this r, and remember, we have for an ideal gas, we're going to use this result that we have for an ideal gas, which is that Cp minus Cv is equal to R for an ideal gas. And that's going to allow us to substitute here to make a little simplification. So when I can rearrange and put just the temperature dependence on this side, the volume dependence on this side, and now I'm going to have the ratio of Cp over Cv minus 1 as the multiplier here. And then taking the anti-log of both sides, this becomes TF over T final over T initial, I'm sorry, is equal to V initial over V final raised to the power of this quantity here, and I'm going to substitute in, identify gamma as the ratio of the constant pressure heat capacity to the constant volume heat capacity. So our ratio of T final over T initial is equal to V initial over V final raised to the power of gamma minus 1. All right. So this one was trickier, and we were able to, to work out using, the first law and some what we also know about heat capacities to get this expression here. And if I take that expression and I use the ideal gas law, again, PV equals nRT, I can from this expression derive this expression here, and then do a little rearranging, and that becomes P initial V initial to the gamma power is equal to P final V final to the gamma power, and that is our expression for adiabatic expansion. And if you remember during isothermal expansion, which is Boyle's law, we had P initial V initial is equal to P final V final. So you can see the difference between these two types of expansion. In the isothermal expansion, we're expanding in contact with a bath where heat is able to flow in, and V initial is equal to P final V final. That's Boyle's law. But for the adiabatic case, where no heat can flow in, and as the piston expands, we get work out of the system and the temperature drops, we end up with this expression there for the dependence on the initial and final states. All right. So we can also then go ahead and use this expression to get the whole change in temperature. Remember I said that as the gas expands, it's going to do work. The energy is going to go down because it's lost that energy through the work, and the temperature should go down. How much does it go down? Well, we can use this expression up here to find T final minus T initial and substitute in. We'll get this expression here. And then finally, to get to work, well, we could have used just minus P dV integrated, but we can also get it from the temperature by using the integral of CV dt from Ti to T final, which we can pull the CV out if we assume that it's approximately temperature independent, which is absolutely true for the ideal gas. And then we have this integral here, which becomes this, which then finally simplifies to this, and this is our work that we get out. So we're able to get then a number of expressions understanding how the temperature varies in adiabatic expansion, how the pressure varies in an adiabatic expansion, and what the work that we get out is in this case. All right, so now we're going to come to a little bit of a brain teaser here. We're going to look at an irreversible process, and what we're interested in is something called the Joule expansion experiment. And it's a very simple experiment. You imagine you have a gas. So here in this example, I have a bulb that's full of an ideal gas, and it's at 2 atmospheres, and it's connected to another flask of identical volume, and this side is completely evacuated. And now what I'm going to do is I'm going to open up the valve between the two, and when I open up the valve and connect this chamber with the vacuum chamber, then the gas will expand to the other side, and now I'll have a adiabatic expansion. So this is not connected to any kind of bath in this case here. So we're having an irreversible adiabatic expansion in this process here. So remember we talked about what irreversible processes look like, and when I open up that valve, that's definitely going to be an irreversible process as it goes from this state to this state, okay? So the question is, what's the work that's done by the system in this free expansion into the vacuum, okay? Well, it turns out that the work here is actually 0 because the gas is actually expanding against an external pressure of 0. So if you remember that the work that it does is P dV, but if the external pressure is 0, then it's 0 times dV. So it's still, you're going to end up with no work in the process. So that means if it does no work, then, and it's adiabatic walls, then both the heat and the work are 0, then delta U for this process has to be 0 also, okay? And remember, for an ideal gas, the molecules' energies are purely kinetic. There's no potential energy because there's no interactions between ideal gas molecules, and it depends only on temperature. So then that means that if delta U is 0, then delta T is also 0 for the ideal gas during the free expansion into a vacuum. All right? All right, so this might be a result that might kind of confuse you at first, but think about this carefully and you can see that all of these conclusions make sense for this Joule expansion experiment. So for an ideal gas, the bottom line is that the temperature doesn't change. For a real gas, though, there is a potential energy term of interaction between our molecules in the gas phase. So as the gas expands from one side to the other, then there's a change in the potential energy of interaction. So the average distance between the molecules changes. And so there'll be a conversion back and forth between kinetic and potential energy as that distance between the two of the molecules changes. And that will cause a change in the kinetic energy, which will then cause a change in the temperature. So for a real gas, when it expands into the vacuum, we can see a change in the temperature, whereas in an ideal gas, we won't. So this change in the temperature is purely due to the potential energy of interaction between the real molecules in the gas phase. And in fact, Joule actually tried to measure that change in temperature when a real gas expands into a vacuum, but his early experiments didn't work so well. He wasn't able to actually measure the temperature change of the gas when it expanded into the vacuum. But later, working with Thomson, Lord Kelvin, he was able to design an experiment called the Joule-Thomson expansion experiment, where they actually did an isenthalpic experiment where they were able to measure the kind of temperature change that would occur in this type of experiment, but it was in a different setup. But I'm not going to get into that for this course, but certainly if you read more about Joule-Thomson expansion, its origins come in sort of this thought experiment here. Okay, so that's it for this lecture. In the next lecture, we're ready to start looking at the second law of thermodynamics.